Hello students, in this video we'll discuss properties of the Moore-Penrose inverse. Let's recall that if we let T be a mapping V into W, where V and W are finite dimensional inner product spaces, define T sharp, okay? And T sharp is going to be a mapping that goes from W over here. It's going to be a mapping that goes from W, the range of T, onto the null space perpendicular of T by T star is equal to T restricted to the null space of T perpendicular inverse times the projection onto the range of T, okay? And so now, of course, we want several different properties of this, and so let's talk about some properties. So here's a proposition. Let's consider T, T star, and T star T. Well, what can I say about T, T star? This is going to be the projection, the orthogonal projection onto the range of T. And this is going to be the orthogonal projection onto the null space of T perpendicular, okay? So how do I prove this proposition over here? And this proposition is going to be useful in showing that the Moore-Penrose inverse, of course, is the Moore-Penrose inverse, Moore-Penrose Pseudo-inverse. Okay. So let's check this first condition over here. We can call this A and call this over here B, right? So how does the proof go? The proof of A, well, let's suppose that you're perpendicular to the range. So if a vector, I'm going to input things over here in the space W. So if W is perpendicular to the range of T, then what's going to happen when I plug that in, when I plug that W into T star of W will give me 0, right? And so if I plug in W into here, I'll get a 0, then a 0. So in other words, that tells me that T sharp of W is equal to 0. Like that, okay? And then B, so we need to prove the opposite direction of A first. Let's do the opposite direction of A. So in other words, if W is now in the range of T, okay, that means that T of some vector V is equal to W, right? That's exactly what it means to be in the range of T. Now, when I plug in W into T star, what happens? Well, I first project it onto the range, but W is already in the range. The projection does nothing. And I just do what is the inverse. Now, of course, the inverse of this thing, what will the inverse of that map W be? So this V cannot be in the what? I'm assuming it's not equal to 0. If it's 0, we already know that case, right? So if W is not equal to 0, then we're not in the null space over here. And so that tells me over here that T of T star of W is going to be what? It's going to be the V. That's going to the inverse of that thing is going to be the V. So that's going to give me just a W, right? So I just project onto the range. Gives me a W. Okay, excellent. Because this thing over here is exactly that V, right? So let's circle that to make sure it's very, very clear that this V over here is the same thing as this thing over here, right? So that's exactly what we get. Excellent. That proves part A. Well, part B. Okay. First, let's start in the null space. If V is in the null space of T, then T of V is going to be equal to 0, and this says that T of V is equal to 0, and therefore T star, T sharp, T of V is going to be equal to 0. And if V is in the null space perpendicular of T perpendicular, this implies what? This implies that when we do this operation over here, then what's T sharp of TV going to be? So I have T sharp of TV. Well, TV is in the range, right? So when I plug that into the range over here, I'm going to just get TV back out. And now T sharp is going to be the unique element over here. So that's just going to give me V, right? Excellent. So in other words, if you're in the null space perpendicular, you output V. And so that tells me that T sharp T is the projection onto the null space of T perpendicular. Exactly. Great. So that proves this first proposition. Now this proposition is very, very useful in the following sense. So let's do this next case. The next theorem we want to prove is the following. Here's our next proposition. Okay. If we do the following, if I do a t sharp t, what will this be over here? Well, now if I look over here, this is really what? That's really the projection onto the range, so I claim that this is equal to t over here. And then if I do this over here, if I do t sharp, t sharp, then look over here, this is the projection onto the null space over here, so this should be the same thing as just doing 2 in a row, right? So this is going to be just t sharp over here, right? Great. So how do we prove this proposition? Well, we prove this proposition by, I need a lemma to do this first. Just a relatively straightforward calculation over here. So here's a lemma first. So a lemma. So what is the range of t sharp? Okay. Well, the range of t sharp, since it's 1 to 1 to 1 to, is just what? By definition, just the null space of t perpendicular. And then the null space of t sharp is just going to be what? The null space of t sharp is just the range perpendicular. So it's everything's perpendicular to the range of t perpendicular over here, right? Great, so that's my lemma. That's just going to help us. That just stems from the fact that this t sharp is going to be a 1-to-1 and onto transformation, right? Great. All right, good. And so now how do we figure out this proposition over here? So now the proof of the proposition goes as follows. Proof. Well, again, what's the key over here? The key over here is that this thing over here, so t sharp, so t sharp, and then t is really just a projection onto the range of t, projection onto the range of t. But if I have t first and I project onto the range, I've already been projected onto the range, so that's exactly just equal to t, right? And then 2, if we have t star, t, and then t star, I do the parentheses like so, then what do I want t star t? This is the projection onto what? Onto the null space of t perpendicular, like that, t perp, times t sharp. But what's the whole point? The whole point is that once you do t sharp, you land automatically where? You land in the null space of t perp, so this is just going to be t sharp. And so oftentimes when you talk about generalized inverses, you see the requirement that this proposition, they say the generalized inverse is something that has these 2 properties over here. So in other words, the Moore-Penrose inverse is defined like this, satisfies those 2 properties. Now what's the last proposition we want to talk about? The last proposition is that if you do the Moore-Penrose inverse, pseudo-inverse twice, you get back to the original operator, right? So here's the final proposition. Is that t sharp is just equal to t, right? So let's write this out and figure out why this is true. So the proof is as follows. Okay. Of course, we can do this sort of in phases. So what is t sharp? Let's just write out what the definition is, right? It's going to be t sharp restricted to the null space of t sharp perp inverse. And then times the projection onto what? The projection onto the range of t sharp. The range of t sharp, like that. That's exactly what the formula is. Now, what do I know? I know the range of t sharp is the null space of t perpendicular. So this thing over here is the same thing. This projection over here is the same as the projection onto the null space of t perpendicular by the fact that the range of t sharp is the null space of t perpendicular. The null space of t, now this thing over here is what? The null space of t sharp perpendicular is what? Is the range of t perpendicular. So the perpendicular of the perpendicular is the perpendicular, so this is just the range of t, right? Now what is t sharp on the range of t? T sharp maps the range of t into the null space of t perp, and that's the projection into the null space of t perp, right? So let's think about what's going to happen over here. So if I plug in any v, so what's going to happen over here? So now we're going to do 2 cases of our proposition. So let's finish out the proposition. So there's 2 things to consider over here. So the first thing to consider is this. If v is in the null space of t, then what's this t sharp going to be? So t sharp of v. Well, I'm going to project it onto the perpendicular of the null space, right? So if I plug in something in the null space over there, it's going to be mapped to 0, right? And so I just project that to 0, and so this is going to give me a 0, which is the same as t of v, right? That's good. And now if you're perpendicular to the null space, so if v is perpendicular to the null space of t, then t star t of v is going to be what? Well, I know that T of v, if T of v is equal to W, T of v is equal to W in this case, where W is not equal to 0, right? And so then what will happen over here, I'll project onto the perpendicular null space, which v already is, and then I'm going to do what? Then I'm going to look at the inverse of this T sharp over here on the range of T. Well, on the range of T, what do we know that T sharp is? We know T sharp of W is going to be equal to V, right? So this is going to be exactly equal to T sharp of T sharp. It's just going to be the W. So in other words, T of T sharp of T sharp of V is also equal to W, and that proves that T sharp, T sharp, T sharp, T sharp is equal to T, because it agrees on both the null space of T and the null space of T perpendicular. So by using these orthogonality relationships, we're able to conclude a variety of different things, namely that if you do the Moore-Penrose inverse of the Moore-Penrose inverse, you get back to the original underlying operator. And then we have the more classic proposition, which says that typically a pseudo-inverse is defined by saying that T pseudo-inverse, T is equal to T, and T pseudo-inverse, T pseudo-inverse is the pseudo-inverse, right? So this proposition over here is valid for the Moore-Penrose pseudo-inverse, and that allows us to conclude that this Moore-Penrose pseudo-inverse is the right candidate for a pseudo-inverse in general, and we'll also see how this pops up relative to the singular value decomposition in further videos. Thank you very much.